Now that we've got the product and quotient rule down, we're going to add another rule, the chain rule. Incredibly useful, sometimes confusing. We're going to use the chain rule when we have composite or nested functions. So this is a function within another function. And we've been very careful to this date with our product and quotient rules not to show you something that would require the chain rule because we didn't have the tools to deal with it yet. But now we do. So I'm using F and G up here. That's very common for high school. We're going to actually switch over to, I'm just going to highlight that. There we go. We're going to switch over to U and V pretty quickly. It doesn't really matter. These are just kind of letters that we use to assign a function. All right, so how do we identify one? Well, you got to look at what's going on. So let's look at number 1 here. And I want to find the inner function. I'm going to underline the inner function in gold. So I see a couple of things happening. I see sine, and I also see 3x. The sine is being applied to the 3x, so my inner function is 3x, and my outer function is sine. And sometimes we like to say maybe u could be 3x. Substitute u for that function, and v could be sine of 3x or sine of u. I'm going to switch this pen out. All right, we've retired the Galaxy pen and gone with silver just for being able to see it. So we're going to move down to number 2 here. We're looking for the inner function. So we're just looking what's going on. So I see a polynomial, the 4x squared minus 3x plus 7, and I see a power. The power is being applied to the entire polynomial, so my inner function is this. I could say that u, if I want to do a subjob, 4x squared minus 3x plus 7, and then v, I'm just going to get a little circle, is that entire polynomial to the power of 4. So v is u to the power of 4. Getting a little more complicated, for number 3, we have 4 onto a lot going on. So what I'm going to do is going to do some of the things we already know about from previous classes. I'm just going to rewrite that square root as an exponent. I find it's easier. We're going to do that anyway. We can see what's going on. Okay. My inner function, I shouldn't have written it in gold, is obviously x squared minus x. So we have u equals x squared minus x. And we have v is once again going to be the power, or the root, u to the 1/2. And we have a constant in front. We can bring it along for the ride. We could put it v equals 4u to the power 1/2. That's fine. Or you can set it completely outside as long as you remember to bring it back. Moving on. Little trickier ones. Oh, this is the number 2 again. Well, let's make that 4. Here, I've got a few things going on, and we'll absolutely have to deal with this. I have an inner function with an outer function, but then I also have multiplication going on. So if I want to find the derivative for number 4, I'm going to have to do a couple of things. I'm going to have to use a chain rule and the product rule. Which one do you do first? Well, deal with the chain rule first because you're going to need, for the product rule, the left side or derivative, and also, I mean, order of operations, exponents before multiplication. Think of it that way. So looking on our side, we saw that the 4x plus 5 was the u. The power of 3 was the outer function. We find this derivative, and then we go back and apply the product rule. It can be lots of writing. Looking at number 5, let's sneak it here. I kind of have a constant, 4 over 3. That's all right, so I might rewrite this one. 4 over 3 times 5x minus 6x squared to the power of negative 3. So we're still using those negative exponents to set ourselves up for power rules or chain rules, as it were. And looking at this, we don't have anything other than chain rule, inner function, outer function. Our last one, we haven't dealt with e yet. We may or may not, depending on which course you're in. But the inner function in this, because we're doing e to the power of 3x plus 1. That makes it the inner function. U equals 3x minus 1, sorry, not plus, and v is e to the u. So learning how to recognize a composite function is super important. All of these formulas shown here are the same thing. We have one, this is the one you get on your formula sheet. This is the one I tend to use more often. And this is another one that you see more often if you have done the chain rule in high school calculus. They like their F and G's. Okay. Basically, what is this telling us? The easiest one for me to see really is this one. I'm going to take the derivative of the outer function with respect to the inner, and I'm going to multiply it by the derivative of the inner function. So this is a two-function situation, but the beauty of the chain rule is you can just keep going and going and going and going. So what I like to think of it as is a rule that, you know, as long as we get all the derivatives in a list, we can just multiply all those derivatives together, and then we will find the overall y prime, the total dy dx. So how do we do it? Identify the inner function. I have y equals 3x squared minus 3 to the power of 4. This is the inner function. I'm going to call it u. And I'm going to find the derivative of that, du or u prime. And that's a polynomial. We already know how to do this with just a power rule. Excellent. Okay, and now I'm going to identify the outer function. I'm going to call it v. We could just call it y, but we're going to call it v. And it happens to be the u to the power of 4. So I know that means the derivative of something to the power of 4 is simply 4 times that something to the power of 3. And now I can replace u with its value right here. 3x squared minus 3 to the power of 3. So I have u prime and v prime, which is with respect to u, and that goes into my answer. So our derivative is 6x times 4 onto 3x squared minus 3 to the power of 3. And you can rearrange, clean that up. 24x into 3x squared minus 3 to the power of 3. So we see we've stepped the binomial down a degree, and we have maybe more noise than we expected. If we were not using the chain rule, maybe we would have been like, well, I think the thing in front should only be 6x, but it's not, because this is a composite function and you must use the chain rule. Another example, it's almost exactly the same. We have an equation, and when we look at it, we see that it's a polynomial to a power. Our inner function is the polynomial. Let's call it u. If u is 4x squared minus 3x plus 7, u prime is, using the power rule, 8x minus 3. And then we have an outer function, the power of 4. So let's call our outer function v, and we notice that v is the polynomial to the power of 4, but we're just going to write u to the power of 4 instead because it's shorter. And we take the derivative of v with respect to u. 4u cubed. We substitute back in u, so let's get that a highlight. This is going to go back here. That's a very aggressive highlight. And we're going to get 4 onto 4x squared minus 3x plus 7 to the power of 3. Our final answer will have all derivatives we made in our chain. So it needs u prime and it needs v prime to make y prime. We're going to get u prime 8x minus 3 onto v prime. I'm going to put this 4 in the front just because otherwise I might lose it. That's just a style thing. 4x squared minus 3x plus 7 cubed. I'm certainly not going to expand that polynomial cubed. You could 32x minus 12, same. Doesn't change much, but you're definitely not going to multiply that in because you would have to do the binomial expansion as well. Or sorry, the trinomial expansion, which would be gross. So let's leave it there. You might ask, do I really need to write out v prime equals 4u cubed and then substitute back in when it's fairly obvious I get what you're doing? No, you don't. But I'm taking it slowly just so you can see the method that I'm using, and you can work outside to in, inside or out. There's lots of ways to do the chain rule. I'm using this one because we're going perhaps to integration later in this course or in another course where we're going to do substitution, and the UDU comes back big time. And here we have that example from the first page. So in this case, I'm going to do a rewrite. 4 onto x squared minus x to the power of 1/2. So once again, I've got a power going on. My inner function is here. My outer function is the power of 1/2, and I have a constant in front, and you can set that aside, bring it back in, or just combine it with one of the steps, like 4u to the 1/2. Either should work. Just do whatever works for you. So I'm going to find the derivative of our inner function, which I'm going to rename u. u prime is 2x minus 1, and I move on to v. Let's say v is 4u to the power of 1/2. v prime equals 4 times 1/2 times u to the power of negative 1/2. Just stepping down 1. Cleaning up equals 2u to the negative 1/2. Let's put u back in. Equals 2 onto x squared minus x to the negative 1/2. And remembering that could be written as this, x squared minus x to the 1/2, and maybe even 2 onto root, or over, sorry, x squared minus x. Now remember, this is not the derivative of the entire equation. This is not y prime, that's just part of it. So don't walk away before you've combined everything you found. So don't forget about u prime. We're going to combine it with v prime. And then I'm going to go over to the left side here. Y prime equals 2 onto 2x minus 1. So that's just multiplying in over root x squared minus x, which you could also write as 4x minus 2 over root x squared minus x. No need to rationalize the denominator, get fancy. I'm fine with this. And once again, trying to make sure we cover all our bases, that we've seen everything we could possibly see. Let's rewrite this one. 5x minus 6x squared, there's our function, but it's also to the power of negative 3. Identifying the inner function, u equals 5x minus 6x squared. Taking the derivative of that, u prime equals 5 minus 12x. Identifying the outer function, v equals, and I'll leave the 4/3 with this because I will forget it if I put it outside, 4/3 u to the negative 3, which means v prime equals 4/3 multiplied by negative 3u to the negative 4 equals negative 4 over u4, so a different approach this time, but it still works out the same, equals negative 4 over 5x minus 6x squared. I really like having this here because it just makes me look back and not mess it up, to the power of 4. Okay, remember to combine. Here's one thing, here's the other thing. They're going together in the derivative. Y prime equals negative 4 onto 5 minus, and I'm just multiplying u prime times v prime, but because one's a fraction, I'm multiplying u prime into the numerator. Done and done. Or you could distribute the -4. This one's looking ahead a bit. We haven't done trig derivatives, but just for the sake of it, I'm going to tell you that the derivative of sine of a function is equal to cosine of that function. We'll get much more into it, but just for the sake of this example. Okay, how many functions in this one? Inner, an outer function, but an even more outer function. So we have a chain rule that has 3 things. That's fine. We're just going to proceed the same way we did, but we're going to add on a bit. We have u equal to x squared plus 4x, which means u prime, the derivative of that, is 2x plus 4, just by the power rule. We have v is equal to u cubed, which means v prime is equal to, by power rule, 3u squared, setting it back 3 onto x squared plus 4x squared. And now this new thing, w, is equal to sine of v, all that stuff. And if I tell you that w prime is just going to be cosine, to be investigated further later, of v, there we go. So equals the cosine of u cubed. And this is where it's a bit tedious and you can shortcut it if you're feeling confident, is equal to the cosine of x squared plus 4x cubed. So really, we're just putting back in this whole piece. Okay? So our total derivative, this time we need to grab u prime, we need to grab v prime, and we need to grab w prime. We need to make sure we don't have any u, v's, and w's, that all of our variables have been changed or our substitutions have been changed back, so we only have x's, and we go. Okay, 2x plus 4 is u prime. I'm just going to write it down and move it around afterwards. V prime is 3 onto x squared plus 4x squared. And then w prime is cosine of x squared plus 4x cubed. Let's move stuff around. I'm going to bring that 3 out. Maybe I'll multiply it into the 2x plus 4. So I'm going to get 6x plus 12 onto x squared plus 4x to the power of 2 onto cos of, and I'll be a little more careful here, x squared plus 4x cubed. All right, here's our original function. Here's our derivative, much, much grosser. I want to do a couple of examples where the chain rule is going to combine with the product rule or the quotient rule or something else. Okay, so just looking at this, we know for our product rule, I like to do this and have u prime, v prime. U prime is pretty straightforward. It's just going to be 2. V prime is a little more complicated because it's a function within a function. So to find v prime, I need to use the chain rule. So I'm going to build that over here. So I'm just going to pretend that I have this as a single function, that there's no multiplication. I'm just dealing with this part. And I'm going to do everything I did before. Inner, outer. And maybe a little faster, the derivative of the inner part is 4. And the derivative of the outer part will be 3u, which is 4x plus 5. So here I'm kind of being lazy about my substitution, squared, equals 12 onto 4x plus 5 squared. That goes here. 12 onto 4x plus 5 squared. And now I can use my product rule. We start with the kitty corner, u prime v, and we get y prime. Remember, it's u prime v plus v prime u. I hope I said that right. I have no idea. So I multiply these, and then I add the other kitty corner, and I'm building it just kind of so it looks a little better. 12 onto 2x plus 1 onto 4x plus 5 squared. Can you leave it like that? Probably. It depends on what the question is asking. Should you factor out a 2 or should you multiply in the 12? Really just look to what I'm asking you to do. Half the time I forget for clarification, which means to clarify, so you're fine with this, but if I ask you to do something, follow my directions. Take a look at this example. Here we're going to combine the quotient rule with the chain rule. So for my quotient rule, I have u as always a numerator, v is a denominator, u prime, v prime. U prime is straightforward. There's no doubled functions. It's simply the derivative of 1 minus 3x is minus 3. V prime, once again, we're going to pull it over to the side and use the chain rule to find it. The derivative of the inner function is going to be 4x. The derivative of the outer function will be 4u, which is 2x squared minus 1. So once again, moving faster, but you can do it as slow as you want to. There. And we can simplify that to 16x onto 2x squared minus 1 cubed. That goes back up into v prime. Here it goes. Okay, remember, it's important, order matters. In the quotient rule, we have to put u prime v first and then subtract v prime u. So y prime equals negative 3 times 2x squared minus 1 to the power of 4 minus v prime u. I'm going to put the one without the power first, just preference. It doesn't matter if it's multiplication. Onto, I would want to change this maybe. 2x squared minus 1 cubed. Make sure all my brackets line up. There we go, and we're not done. We also need to put that over v squared, which is 2x squared minus 1 to the power of 4 times 2, which makes it to the power of 8. How much cleaning up? This one doesn't have anything that works out nicely. If things could be expanded quickly and gathered, maybe. For me, I would just move the 16x in front so it's easier to see, and then I wouldn't bother with anything else. I'd be like, done and done, good enough. I was testing your quotient rule, not your move around ability. There we go. Let's end with the word problem because they're awesome. So we're going to talk about the energy output of a heater. So remembering that when you let energy be released across the resistance, the change in energy that you release with respect to time is actually the power dissipated. So that's this little piece of information right here. Watts are equal to the change in energy with respect to the change in time. Okay, so we have an equation. The letters are different. That doesn't matter. Let's take a minute. So we want to find E prime, and then we want to find what that value is at 8 seconds. Okay. We are looking at, hopefully, product rule after some chain ruling. So let's do what we can. If t is u, then the derivative of t is just 1. That's nice. And then looking to the second one, we're going to have the derivative of the inner function, which is simply 2. And I'm going to multiply it by the derivative of the outer function. The 2 exponent comes forward. And then I just rewrite the inner function, and I drop the power down to the power 1, not necessary to show it. Okay. E prime is equal to 1 times 1 plus 2t squared, which is simply 1 plus 2t squared, plus, let's say, 4t 1 plus 2t. Now, this is a excellent, even though the question is really just asking you about, power at 8 seconds, and you could just sub in the 8 right now. This is a great question for simplifying because it's not a pain in the butt to do it. Let's expand the binomial. 1 plus 4t plus 4t squared. And then we're going to distribute the 14 to the second binomial. 4t plus 8t squared. Gathering like terms and maybe putting them in the order that I like. 12t squared plus 8t plus 1. And this is totally factorable, but that's not where we're asking for. We're asking for the power at 8 seconds. 12 times 8 squared plus 8 times 8 plus 1, which should give you 833 watts. So what do we know here? We know that we have energy output has a graph that looks like this. We know that any point on the graph, if we want to know the slope of that graph at any point, we use this formula. We know that the slope of that graph, the instantaneous rate of change, will give us the power, which is here.